Okay, sure. Thank you. Thank you for the invitation. Always a pleasure to come back to Cargèse. So, Giulio and Gilles have asked me to give you a few lectures on stochastic dynamics, and in particular, non-equilibrium stochastic dynamics. Okay, and so I'll do that in two sets of lectures, trying to focus on phase transition, non-equilibrium phase transition. We'll get to that in a minute, and the two lectures each. So there's two lectures today, and then two lectures on Monday, I think. And so they will each time be organized in an hour and a half of theory on the board, and then after that is going to be a little bit lighter, and I'll show you examples, typically involving numerical calculation, explaining how the numerics is done, and that will be, projected. Okay, but that's for the second half. Okay. One thing that you will not hear in these lectures is the word spin nor glasses. There is no spin glasses. Okay. So, I know. Okay, so we're going to begin. So I want to discuss stochastic dynamics of several types. But what I will do is I will start with stochastic differential equations, okay? And the lecture is self-contained, so if you have never heard about the stochastic differential equation, I'll try to explain what that is. And for those of you who already know what it is, bear with me. At the end of the day, we're going to cover fairly advanced material. In fact, there's a lot of material to cover, so just, okay? Who knows what the stochastic differential equation is? Okay, pretty much everyone. Okay, so what we're going to look at is, so SDEs. I know I cannot pass this line. So stochastic differential equation. And please interrupt me with question if you have any. So I'll write this. So one of the aims of the lecture also is that I will cover material that is fairly standard in mathematical books, but also not so easily accessible to physicists. I would assume so. Well, maybe I assumed wrong. Like this. Okay. Okay. So in this equation, this is a deterministic drift. Okay. I should for xt takes value in Rd. We're going to look at example where it's in function space. It's in the Hilbert space. So this is a deterministic drift. This B is a vector field that we have, and then this here is the random noise. This is a Wiener process, and here for the moment this matrix will be something that takes value in Rd cross Rd, and this guy will be a Wiener process in Rd. So physicists would not write this equation like that. They would rather write something which is, I think you would use, something like that, and then you would say this is a white noise, so it's a Gaussian process which has zero mean and a covariance, if you look at it at two different times, which is just delta correlated. Okay? I think probably physicists would also write, this is what I denote by expectation, and it would rather be written by a bracket like that, but mathematical books typically reserve that for scalar product, so and use the expectation. Okay. Now there is a reason. I mean, the mathematician can be pedantic, but there is a reason why they write it like this rather than like that, and it's because if you take, a delta t which is bigger than 0, but that says smaller than 1, right? You can discretize this equation. In fact, that's the way you can give it a meaning. And so you can turn it into an iteration rule. Let me quickly write that, which would be everything that I write here actually could also be generalized if these are function of time. But, I don't want to write too many things here. So you can, write something like this. And then here you would get W of k plus 1 delta t minus W of k delta t, something like this, right? And I should put a tilde on this because this is not the same x as before, as above. But what you can show essentially is that if you take delta t going to 0, right, and k delta t going to a fixed t, then the solution to this converges to the solution to that. That's the way you give a meaning to this SDE. Okay? And why do mathematicians write it like this? Is because if you look at this object here, this is the difference of two Wiener processes in law, and so that means equality in distribution. This is equal to square root of delta t times ck, where this guy is IID, so they are independent for different k, and they are Gaussian random variable with unit covariance in d dimension. So this is the identity matrix. Okay? And the reason why this is written like that is apparent from here, namely that if you were to take in this equation delta t going to 0, right? The standard way, you would want to go there is that you would subtract this guy, put it on this side, divide by delta t, take the limit. But you cannot do that because there's a square root of delta t here, so you would end up with a 1 over square root of delta t. And what does that mean? It essentially means that this process xt, the solution, is continuous in time, but it's not differentiable. And in fact, it's only older with exponent 1/2. Okay? This has other important consequences, namely that because this process is not differentiable, it actually matters in which way you discretize this. So here, I have used this guy, right? And that corresponds to what's called the Ito convention, that which will be convenient for in a minute. I'll explain to you why. You would get a different process if you were to discretize this in a different way. So for an ODE, this guy here, you could replace it by k plus 1 delta t. That's the same limit. It would give you, this would be forward Euler, and the other one would be backward Euler, right? It would be an implicit scheme. You could try to do that here too, but that changed the result. You get a different process. And again, why is that? Is because this guy, if you change the delta t it's evaluated to, you putting square root of delta t term, so to all the delta t that change things. Okay? And so there are other conventions that you could do, which is, the one is the Stratanovich, the other one is what's called sometimes kinetic. There are different discretizations there. They lead to different equations. There's simple rule to go from one to the other, so I'm not going to discuss that. I will stick to this. Okay? I forgot to mention that I'm going to go fairly fast to cover the material, but I'm here for the full school, so we can discuss this offline if there's anything that is unclear later on. Okay? So we have that. Okay, so this is like at the level of the processes. Now I'm going to introduce two PDEs. Okay, and the first one I will introduce, in fact, is maybe the one that is you are the least familiar with, and it's called the backward Kolmogorov equation. So how does this equation work? Is that it's an equation for a field U that depends on t and x, and it satisfies this equation. Okay, sorry. Let me go like that. This is equal to 0. D here, this tensor, is the tensor that you obtain by taking the tensor sigma and multiplying it by its transpose. So it's a positive definite matrix, semi-definite in general. This double dot means that it's a full contraction of this guy. So this is like the trace of this tensor times that one. This is the Laplacian. Okay. In a minute, we're going to get a d dot scalar, so it's going to be easier, right? And so this is an equation that you can write, and it has the following property that if you solve it with this final condition, then it implies there's a probabilistic interpretation of the solution, namely that if you evaluate the field so you notice that because this is a diffusion, and I have put it in the left-hand side, it's like anti-diffusion. So to solve this equation, you need to solve it backward in time. You solve it with a final condition. That's why it's called backward. And the interpretation is then that this guy is the expectation of f of xt, capital T. more generally, if you put a little t here, where's my, didn't I have, huh? Oh, there's also, okay. So if you were to put t here, you would get t minus t, but that doesn't really matter. And what this denotes expectation conditional on x at time t equal 0 is equal to lowercase x. I think that my writing is clear enough to distinguish what is capital X from lowercase x, otherwise you should think about an x0. So this equation has a probabilistic interpretation, and we're going to use it. Okay? And there's an operator that you see here, which is B divergence 1/2 D double gradient on U. And that is called the generator. Namely, there's an operator, which is, I'm going to write for any test function G, you can write like this, which is this B. Let me not, everything depends on X, but to simplify notation and go a little bit faster, let me remove them. It's like that. This is this define this L. This L is called the infinitesimal generator. Okay? And it has the following interpretation. You can also derive it as being, it's the limit as t goes to 0 of 1 over t times the conditional expectation over x of g, of xt minus g of x. Okay? So if there were no noise in this equation, I should probably have said that before, this is just an ODE with this drift velocity. Okay? And then in that case, what you would get here is that this guy would be gone, and the generator would be this. And this is consistent essentially by saying that in this case you don't need to take any expectation. And what I would have defined here is just the time derivative of this object. Right? This is the time derivative of g of xt evaluated at t equals 0. And that would simply be b times grad g by chain rule. Okay? So this thing here, which is in fact an instance of Ito formula, is simply saying that when you try to use the chain rule to define what is the d over dt of g, there is one thing that you need to take into account. There is an additional term. Where is this additional term coming from? Is, well, if you, in this guy, suppose that you use the first iteration of this, therefore k, right here k was, you take k equal n, you take the first iteration here. What you would get is that if you Taylor expand everything, you try to do chain rule, there's going to be a term which is of order square root delta t here. So to go to delta t, you need to go to the second order in the expansion. That's what gives you this, in a nutshell. Okay? And that's why you get diffusion associated with this equation. Right? Historically, of course, these equations were introduced before that, and that's just Ito order that went that way. So that's the first. That's the backward Kolmogorov equation. And as you can see, it allows you to evaluate expectations. Okay? Now I'm going to write another one, which we're also going to use quite a lot, and that is the forward Kolmogorov equation, which you guys know, and in fact, me too, more as the Fokker-Planck equation. Let me write this one. Je peux utiliser l'autre. Yes, I know that this is a workout, okay. So the second equation is the forward Kolmogorov equation, which you also know as a Fokker-Planck equation, FPE. Okay, and that's an equation for if you denote rho of tx, this is the PDF of xt, meaning this is the object that is such that if you take any test function g of x, and then you multiply it by rho of tx, and you integrate that, by definition, this is supposed to give you the expectation of g of xt, not necessarily conditional. It could be that in this case, there is some initial, that the xt has some initial randomness. And that guy satisfies this equation. Everything depends on time, so it's minus nx okay, with an initial condition, rho at time t equals 0 of x, which is whatever is rho of x. For example, this could be it could be a Dirac at some x0 if you want, but more generally you could think about that, this is the randomness in the initial condition. Okay? And that one needs to be solved forward in time. Right? Okay. And you see that you can rewrite that as the divergence of a current, where this current is equal to B times, okay, so it's B of x rho of Tx minus 1/2 the divergence of D times rho of Tx, D of x. Okay? And that's called the probability current. And it will play an important role in our story. Sorry, called the probability current. So when you write the equation like that, right, this is like it's written, it is a conservation, it's a conservation law, and it actually guarantees something that, needs to be true, is that the norm of this function remains equal to 1, the L1 norm, as time proceeds. You can also show from this equation that rho remains positive at all times. So it's a PDF. Okay? It's a PDF, and the way the PDF moves is by this current. Okay, so now, where is this? Okay. So now, okay, so now we're going to discuss this notion of equilibrium or non-equilibrium, which is that, okay, so the solution of the SDE has noise, so it keeps moving around, but you could perfectly imagine that you are looking at processes that have a B and a D in such a way that this equation reaches steady state. Okay? What's a steady state? Well, it would be a case, so what would be, a statistical steady state? Right? It would simply be a state in which you have that the dt of rho Tx has stopped moving, so this is equal to 0. Meaning it's a state, it's typically the state that this guy, if you put the right condition as t goes to infinity, would converge towards, say, a rho of x. No more time. Okay? And so what's the equation for this guy? Well, it's just, you can rewrite it like that. It's satisfied that the divergence of j, which is now also something which is independent of time, needs to be equal to 0. Was j is this, with this node independent of time. Okay? And now there are two cases that you could imagine. One is the equilibrium steady state. So if you want to make this equal to 0, right, you can make it in two ways. Well, either you can say, well, this guy is equal to 0. No current. But obviously, there is another way to make it non-zero, is if this condition is satisfied. I rewrite the one above, but you have that this guy is not, so it's divergence free, but it's non-zero. Okay? So these are steady states in which there is probability current. Right? The current is non-zero. Okay? And for most of the lecture we're going to focus on this. But let me just give you a little, one example. What is the classical case of this that you know it? Is that if you take, so here's an example, I'll write it like that for this, right? You can take, the classical example would be that you take b of x is equal to some, you could make it dependent of x, but it's a little bit more complicated. So this is minus some diffusion tensor times the gradient of a potential. And you take d of x, okay, so you take, right, you just take that. Okay, and so d of x equal d. In fact, sorry, let me write that slightly differently. This is a d at, and then this guy you would take kbt times d at twice. In that case, you can convince yourself that the rho of x is just some normalization factor times the exponential of minus kbt minus u of x over kbt. So it's the standard Gibbs state that you have associated with this energy, right? And this guy has no current. It's in detail balance. In the next class, I'm going to elaborate on that a little bit more. Okay? Now, I want to focus for most of the rest of the class on this. These guys. So the case where there is a non-zero current. Okay? So far so good? Okay. And I want to focus on something which is a little bit, so let me write down again the equation. So everything that I explain will be generalizable to this, but I will really focus for most of the lecture on cases where you have a statistical steady state. Sometimes they would not even, we can also look at this outside of statistical steady state, but we're going to look at statistical steady state with current. And what I'm going to do today is look at problems in which we can analyze what's going on by solving variational problems that are reducible to ODE. So I'm going to, this is like a little bit obscure, but let me explain this. Maybe is that today we're going to look at this. So now let me simplify things a little bit. I'm going to keep this B of t, but to simplify my life, and yours, to simplify all lives, I'm going to take that sigma here now is simply a real number. Okay, it's a scalar. So the d is sigma squared. That means that the diffusion coefficient is also just a scalar, and it's just simply the 1/2 of the square. Sorry, it's this. That guy. Okay, and I'm going to do something else, and that is very important. Is that I'm going to scale this by a square root of epsilon. And we're going to look at the case where epsilon is small. So that means we're going to look at what's going on in the small noise limit. Okay, and that will allow us to do large deviation. So this would be, in this case, for example, you could imagine that this epsilon is kBt. You'd extract it from it, right? And so you would look at what happened when you look at something where the temperature is small compared to the energy, if you want to, right? But if you want to do that mathematically, we'll just do it like this. Yes? No, just a constant. It's just to simplify all the notation. Everything that I explain can be generalized to the sigma x. That's a tensor, but it's much easier to look at that. All right. So what's happening here? So, and I'm going to put a little epsilon here to emphasize this that though this process is a process that depends on epsilon. Okay. So let's think a little bit about what's going on. Well, first of all, we can ask yourself, what happens if we let epsilon go to 0? And we look at the solution. So suppose we fix a certain time interval, 0t, and we look at this process on that time interval, and we let epsilon go to 0. Okay? Then what happens is that you have that x epsilon of t converge towards xt, where this xt simply satisfies this ODE. The impact of the noise disappears in that limit. And that statement, if I want to precise it a little bit, you could say something like that. You could say that if you take, for all t that are less than infinity, if you take the absolute value, but difference of the absolute value, you take the sup of that, or the max if you prefer, over all possible times. Okay, since it's continuous, I could replace that by a sup. Then you take the expectation of this stay starting at x, right? Then this goes to 0 as epsilon goes to 0. That's the meaning in which, for example, this you can prove other statement, but that's one way. That would be, and this is a statement which is kind of, it's a law of large number, if you wish. In a sense that you could think about this as the average of the process, and this, in a sense that I'm going to explain in a minute, and this is the noisy version. Right? Now, okay, so, you know that if you have done a little bit of probability that if you want to go below the law of large number, you can actually do CLT. So what would be the CLT? It would be you take x of t epsilon, you subtract xt, so this guy goes to 0 now, and to get a non-trivial limit, you scale it up. And how do you need to scale it up to get the CLT scaling? You scale it up by square root of epsilon. And you say that this is eta epsilon t. You define a new process, which is simply the original one minus its limit divided by square root of epsilon. That's exactly the same thing as what you do for CLT. And then what the CLT would say is that this guy, as epsilon goes to 0, in some sense converges to a process eta t, that you can define what the limit is. And this satisfies, it's a solution of an SDE with linear coefficient and additive noise, where all of these guys can be function that are function of xt. So it's linear in eta, okay? But they could depend on the process. And that's a statement about, so this is, this is the law of large number, and this is a CLC statement. I'm not going to elaborate on this and write you the equation for there, because you realize immediately something when you look at this, is that this guy doesn't influence xt. Okay? You can solve this equation, that's the law of large number, and then if you want to know what are the fluctuations around the law of large number, the fluctuation in the scale of the CLT, you can look at this variable, look at this limit, and analyze this equation. Okay? But why is that not satisfactory? Is because I'm going to make a little picture maybe at the end over there, or I'll put it here. Why? I'll get used to it. So why do we want to? Why are we not necessarily happy about this? Is because you could imagine, here I'm going to draw something, and we will revisit this. Imagine that the flow line of the CLT are something like this. So imagine that you have, what I'm drawing here is a little picture of the flow lines, like that, up. So what these are the flow lines of x dot t is equal to b of xt, the law of large number. Okay? And the little picture, so it could be in d equal to d. And the point that I want, why did I draw that is because I want to make the point that there is a stable fixed point here, and there's a stable fixed point, but there's two of them. And there's an unstable fixed point in the middle. Okay? We're going to discuss example later on that have precisely this feature. So if you look at this, right, there is the following feature that if you were to look at the CLT, it will tell you how, on short time scale, this guy will actually, the solution of the original process will actually follow these things, but with a little perturbation around it, and then it will go there and kind of hover around it for, not going very far, because it's going to be in a scale square root of epsilon. But we know, that eventually there will be a large fluctuation of the noise that might push the solution from here to there and from there to here. And in particular, you may want to know whether the fluctuations that do this thing are more likely than the fluctuations that push it back. If you knew that information, you would be able to tell in the limit as epsilon go to 0 which one would be the preferred state over the invariant measure of the process, or the non-equivalent statistical steady state. And this information is not available to you neither from this nor from this. We need to do something else. Okay? Okay, so how can we do that? Let me write it here. Well, and this is why I started, we're going to do another process if I have time in the first part. I started with this, right? Is that, okay, if you go back to the discretization of this guy, you realize that the x of t plus delta t, conditional on its past, is a Gaussian. That's because this guy is a Gaussian. In fact, x of t you can write down, right? So if I go back, so this is what we want to look at, but let me now go back to this. We know that x of t plus delta t, conditional on xt, is, what is the distribution of that? This is little wiggle. It's a Gaussian random variable which has what? A mean b of xt times delta t, and a variance which is also delta t times sigma squared over 2. That's because this guy here, actually, sorry, epsilon, that's important. That's because this guy here has Gaussian increments that are independent. Okay? And so if you use this observation together with the fact that it's Markov, meaning that you can pile up, you can formally write down something like this. You can write down that you can write down a path measure. And I'm going to derive this thing, or give a meaning to it in another way. So this is, if you wish, the probability density, which doesn't make any sense mathematically, but of a given path. Okay, that's what you would write down if you write at discretized level, and you use the Markov property, and then you telescope all of these things. You rewrite as a group. You're going to get something which is like this. Okay. In particular, this would mean that formally, right? And I'm going to explain. Suppose that I were to look at the expectation. I'm going to explain why I take this. Here t, is again a fixed time, right? If you were to look at this, then, okay, let me make myself a little bit more space. You would be able to write that formally as a path integral of the exponential of this guy plus 1 over 2 epsilon f of xt. This is the meaning what I write. So this would be like, a path integral. So this doesn't make any sense, and I apologize if there are mathematicians in the room that in fact what we should really do here is interpret it using Girsanov theorem. We're not going to do that. I can do that offline if you want, because we're going to go into another way. But I want to look at this expression, right? And there's a good moment to pause to see if this actually makes sense to you. If we were to discretize time, you would replace this integral by a sum over the discretized time interval, and then everything would make sense. Okay? It's just that taking the limit of that is complicated at this level. Yes? Is this clear, this path integral? Okay, so I'm asking question about without that guy, then I'll get to that guy in a minute. Is the path integral sort of clear intuitively? I need that just to try. I'm trying to give you intuition here, because there's another way to derive this that is more proper. Oh, that's right. Sorry. That was what I want. Okay. Now, you notice that I have introduced here an observable, and we're going to use that in a minute when we go back to the backward Kolmogorov equation, which is an observable where I have put the 1 over epsilon the 1 over epsilon in. Okay? And the reason why I want to do that is because if you were to take the expectation over normal observable that do not depend on epsilon, they would be dominated simply by either this or this, mostly this. This is a way to look at an observable where this integral is actually dominated by points that are not the solution of this equation. Let me try to explain this a little bit better. This path integral, as I say, doesn't make much sense mathematically. But it should remind you of something. This is an integral that involves the integrand here is the exponential of 1 over epsilon times something. And we are looking at what happens when epsilon goes to 0. We want to look at what's going on for small epsilon. Yes? And so, or I passed the line, sorry. You know that one way to evaluate integrals where you have this small parameter is to do Laplace method. What is Laplace method? The way you should do this integral here is to you should essentially talk here, okay, this is no longer a process. This is like a dummy integration variable. So if you were to perform this, like what you should do is generate path, okay, not from the SDE, just path, and this would give you what is the probability weight. and then you superpose them. When epsilon is very small, this expression tells you that, well, actually, among all of these paths, there's only one that essentially will dominate the whole integral, and that's Laplace method. So if you do Laplace method, what does Laplace method tell you? And we're going to rederive this in a minute. Laplace method says that, it says the following thing. It says that if you take this expectation, you take the log of it, you multiply it by epsilon, then this guy is a limit. And what is the limit? So if you take epsilon going to 0, well, the limit is what maximizes the integrand here. So it's the sup of the integral, let me write it in that order. What's the sup? What is the sup? Since I'm start at x0, it's a sup over all possible xt, but they need to be that at xt equals 0, this is equal to x0. I forgot to tell you, I wrote note about this, and I'll make them available, I don't know how, but so you can, all the formula, probably with many misprints, will be available to you, and so you can look at the formula, try to find the misprints, come back to me, and you'll get a sticker for every misprint, okay? So we have this guy. And so what we have done is that using Laplace method, what we have obtained here is that you can replace the calculation of an integral, in this case a path integral, which really is the calculation of an expectation, into an optimization problem. And that in principle is simpler. So we're going to focus on that. In the next half of the class, I will show you example where we can do this. Okay? Now, why is I mean, it's not simpler to perform, because clearly, if you were to do standard numerics, you could, just simulate many paths of this and try to calculate the expectation of that object. Okay? If you do that, it's very easy to do, because there's essentially nothing else to do than just using Euler-Maruyama scheme to simulate this guy, and then just, replace the expectation here over an empirical expectation over all the solution that you have generated. But if epsilon is small, in general, it would fail miserably, because what you would get is that the path that you generate are typical path, so you would essentially generate this plus a little bit of that, and they would not contribute to this expectation much, which means, in plain term, that the variance of the estimator that you get with this naive Monte Carlo estimator would be dramatic. Its mean is kind of much smaller than its standard deviation, so you need, in fact, a number of realization which is exponential in epsilon, if epsilon is small. You can't do it. You need to do important sampling, but here we not do any sampling. We're just replacing this whole sampling by this supremum here. Let's elaborate a little bit on this. You're very quiet, which either suggests that I'm extremely clear. Typically, that's not the case, or that you are a little bit lost, which would be my fault. But please ask me questions if yeah. There is no 1/2. I'm also dropping a few misprint on the board just to make sure you're remaining attentive, okay? Yes? This is only at x at one time. On all times. Yes. Then you would have a function, there would be a time integral here. Okay? It would change what I'm going to write that down. But you can do the same thing because it's a path integral. Okay? I'll get to that in a second. Okay, so you notice that this guy here is this is like a Lagrangian. Well, if you include this guy in the two half, the one half, right? This is like a Lagrangian of x dot, and so you know how to write down the Lagrange equation for this. It's that you take the derivative of this guy with respect to x dot and then the time derivative of that. Let me write it. Right? You know, if you want to do this optimization, you need to take d of this, considering these the xt and x dot t as being independent, and then you take the time derivative of that, and this needs to be equal to the time derivative with respect to xt. This is the standard Lagrange equation, right, that you probably have seen in mechanics. Now, how is that derived? Just to remind yourself, is that, well, this is a convex function in x dot, so it has a unique minimum. So what you need to find is, like, at this minimum, the first variation around the minimum vanishes. So you can calculate the first variation of that. And if you calculate, that means you change x into x plus dx. Okay, then you expand, you look at the linear term in dx. Why do you get this extra dot here? Is because when you take the variation with respect to x dot, you get the x delta x dot. And so to make it proportional to delta x, you need to integrate by part. Okay, that's the way you get the Lagrange equation. And so this is important here because, okay, so let me write down what are these Lagrange equations. Let me write them. Is that is equal to minus the gradient of b, this, okay, so this, if you look at that for this specific problem, this is what you get. Okay, this is about this part that is equal to 0. But then you notice that okay, so when you do the first variation, there is no first variation here because the initial condition is specified. So this has to be solved with x at time t equals 0 equal x0, the initial condition. But to get there, you notice so far we have not seen the f. Where is the f? Well, the f actually will enter, because what happens is that when you take the variation here with respect to x, the x dot, and you integrate by part, the boundary condition from there doesn't exist. There is no variation at x0, since delta x0 is equal to 0, since I know that. But there is a variation at that point. And so there's a final condition that you need to have, which is that you need, this matches that. So let me write this. So what you end up having is like Euler equation, but as a boundary value problem. Okay, everybody sees where this is coming from? This is matching the fact that my xt at capital T is free. I can do variation, but that's what fixed this. Okay, we'll look at other boundary condition in a minute. So, we have this guy. Now you notice that, okay, so this, we're going to discuss numerics in the second half of the class. We need to solve this equation. You see that to solve this equation a priori is a little bit complicated, because it's like we know we are in the realm of classical mechanics in a way, except it's a different type of Lagrangian. But you need to solve it not with an initial condition over xt and an initial condition over x dot. Is you have a final condition, right? Initial and final. Really complicated. But you notice that there is something you can do here. I'll do that in a minute. It's not going to simplify what I'm saying, but you could declare that this here, okay, is equal to a new field. I'm going to call it theta for a reason that, okay, whatever. This is the conjugate momentum, theta, not theta dot. Suppose I define theta dot to be this guy. Theta. I said, don't listen to what I say, look at what I write, and sometimes listen and don't look. Then you get this. I can rewrite the equation there like this. Okay, so now I think actually what I want to define this to be sigma squared times theta, so that this is theta. Okay? And so the other one gets this. So this is a tensor, right? And typically this is, typically what you write is that what is this guy is dbi over dxj, but here I need a transpose of that tensor, just little remark. And so you get this, and now you have a final condition. So it's still not, not the standard Euler-Lagrange equation, but now you see that, so this is like a conjugate momentum, right? I have the sigma squared that is now over here, right? And this is the Lagrangian form of the equation, and this is the Hamiltonian form of the equation. And it's a boundary value problem. So we're going to discuss numerics, but you could, for example, do a procedure that's fairly simple, which following iteration, you start with x0 and a guess for theta, say theta equals 0. You solve this equation, you store the path, and then you solve it forward in time. Then whatever that is give you a final condition here. You solve this one backward in time, and then you loop upon this. Okay? And under a certain condition, this will converge and give you what is the optimal path. Okay? Now, okay, so we could, and I'm going to, now let's go back to this example. There's a reason why I took this, and I'll get back to it in a minute. Okay, so there's a few formula here that I need to write before we proceed, which is that, I'll write that in a minute. Use this here, okay, is I can rewrite this equation plus the boundary condition like this, right? This is the standard Hamilton's equation. And what is H here? Well, H is the Legendre transform of this L, as you know, right? So what is H of x theta? Is the sup over y of y times x minus L of x y. Okay? In this specific example, it is given by this. And you can check that the equation that I have written there are the Hamilton's equation associated with this Hamiltonian. The reason why I want to insist and we want to look at this Hamiltonian form is that I'm going to derive it in another way. And in fact, it can also be used in situations in which the noise is non-Gaussian, and as a result, the path integral that I write is not available to you, and you need to derive things in another way. And in that case, we can derive the Hamiltonian, but in general, finding the Lagrangian, which is both these functions are convex in y and x, so you have the involution property of the Legendre. That's right. See, that's like you're paying attention. It's good, 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 good. So we're going to look at cases in which H is available to you but not L. So these equations are available to you but not this form in a minute, if I get there. Okay. So before I go there, let's look a little bit about this example again. Okay. So in this case, I have described that with this guy, but you could imagine that you may want to look at another problem, which is imagine that I want to look at the probability that x, so I'm going to draw that here, that if you start at x, that x at time capital T is in some set B. The little picture here, let's imagine that this is the flow in this case, there would be only one stable fixed point, let's say. This is again the flow of x dot is equal to b of x, which is always, by the way, what you obtain if you look at this equation at theta equals 0. I'll get to that again. And let's imagine that there's a set B here, right? In this case, you would change this boundary condition here into saying that you want that x at time t equal capital T belongs to B, meaning is equal to some x1 that is in B. Because if you go back to the path integral, right, in this case what you would need to do is that you should condition over all paths that are such that they end up in the right set. Okay? And so typically that would give that, you know, the solution of the equation would be something like this, something that you would not see neither from the CLT nor the law of large number. It would do something like that, and it would end up here, you know, at this x. This is not the same as this. Now let's put it a little star maybe. At time t, it would be, you know, this x1, which is in general in the boundary of B. And you would have to solve this thing. Okay? Now there's something here that is a little bit complicated, that, right, is that you can also try to understand how to go from this state to this state. Okay? And let me try to explain that. So let's imagine that this guy here is denoted as x minus. Let's say that this is an xs and this is an x plus. The k that will matter are really these two guys. So let's imagine that you have these two quantities. Okay? Then, okay, so what is the problem that we are solving here? We have solved, suppose I look at this, all xt, which are such that at t equals 0, it's at x minus, and at xt equal t is at x plus, right? And then I'm going to write, okay, so, you know, I'm rewriting the Lagrangian in another way so that we will because this, I'm just rewriting, this guy here is just L is the integral from, by this definition, it's equal to that. So it's the same thing. So this is the problem that led, you know, to this where I specify x1, right? I change this x0 into x minus and this one into x plus. Then you would get that. Okay? But let me add another little twist in it, which is that add. So I'm adding this guy. You not only look at all paths, but you also look at the path. Among all paths, you optimize over time. Okay? So in the notes, it's explained that at the end of the day, this is equivalent to solving the system at h equals 0. I'll maybe get to that in a minute. So it's, and I'll show you that an example. But it's not very important for the. This defines something which is a quasi-potential. It's a function of two arguments, x plus and x minus, which in fact you can define for any pairs of points in your space. I just specialize it to these two guys, but you could define it everywhere. And this is something which is called a quasi-potential. I'll show it to you in the next lecture, okay, on an example. You will see it in real life. So this is the non-equilibrium equivalent of the potential, right, the U that I described in my little example. And in fact, it can be used in the same way to deduce Arrhenius' law. Okay, so now I need 2 minutes to explain this. Okay, so first, let's be clear about something. In general, this vector field here is not in gradient form. It's not minus the gradient of a potential. Okay? That means that this is a non-gradient system. This is not, I mean, if this was minus the gradient of an energy, if this quantity was minus the gradient of an energy, then these flow lines would simply be steepest descent flow over that energy. And this picture would then mean that there is a local minimum of the energy there, a local minimum of the energy there, and a saddle point in between here. Okay? And in that case, Arrhenius law would tell you that with a little bit of noise or small temperature, the rate at which the system would go from here to here would be exponentially depending on the energy barrier between these states. And conversely, the rate to go from here to here would depend on the energy barrier that you need to, hop over to go there. Okay? In these systems, you can't do this, at least not that easily. You cannot read off energy barriers from B, because there is no energy associated with it. But you can still read off energy barrier from here. In other words, what you can show is that the rate to go from minus to plus, or x minus to, okay, so let's write it, okay, I think it's clear. This rate is, this means up to prefactor, the exponential of minus 1 over epsilon v of x minus x plus. What does little wiggle mean? It means that the equality is true in the limit if you take the log here and multiply by epsilon. Okay? So this is this guy is my epsilon, right? The sigma is in the sigma is now included. The sigma is included in the here.
Okay, so it's inside.
Yes. Because in general, there is no temperature, and right, it's just the scaling of the noise. I'll explain that in a minute. You'll see why. Okay? And so now you have, you can calculate these, and of course, you have the opposite one. If you want to go from plus to minus, you need to calculate this guy. So you need to solve this optimization problem, and I'll show you how to do that. Okay? So this is a generalization of Arrhenius law for non-equilibrium system. Okay? And we're going to discuss that next time. But, okay, so what does equilibrium mean? It means that you have microscopic time reversibility. If you have microscopic time reversibility, it means that, and this is why these calculations are so simple, is that how does the process by a large fluctuation go from there to there? Well, the noise needs to push it at the separatrix. But once it is at the separatrix, no noise is needed to do the rest of the process. So you always know, the process goes down from the separatrix. It needs to do that. If you are in detail balance, and that's my second class next week, if you know the process go forward in time, you know it goes backward in time since everything is time reversible. So you can automatically deduce that, but that means that the way it went up from here to here is the way it went down time reversed. But here there is no up and down, there is no potential. There's only, the B is not the grain of the potential. So you need to calculate what the optimizer here is. And I'll show it to you after the break. In general, it's a trajectory which is not that. It could do something like this, for example. I'll show you that this is actually what happened. Okay? And then, if you calculate along this path these objects, you would get the V that you need to deduce what's the rate. And if you do the other one, well, typically you would get something different. You might get a path that now do I don't know, this, and then go down that way. And that would be the path that allows you to calculate the quasi-potential to go from x plus to x minus. Okay? And you need to calculate both. And I'll show you how to calculate that in the next class. Right? So this is this. Yeah. I mean, it could be that you have the noise that depend on space that are degenerate in such a way that this trajectory would have to go here, for example. But then what it would go from there is essentially go that and that. Okay. So, yes. And it could be that sometimes it does that and then, right. So there, I'm just drawing you the simplest case where it goes to this XS. Notice that, and that this, of course, the formalism apply in all cases. This is a very special case, because if you are in dimension bigger than 2, for example, and this is not a gradient field, the dynamics that you get x dot equal bx could be very complicated. It's not guaranteed that it has fixed point. It could have attractors. It could be chaotic. This still applies, but we're going to focus on cases that are like this. Okay? I don't know how I'm doing with time. Not so well. Okay. So we're going to discuss this a little bit. Yeah? Yes. Okay, so let me discuss this very briefly. You see that there's this double minimization that you need to, and I'll show it to you with example in a minute, but you need to do this. One way to do that is that you can introduce a new time, which is tau, this guy. Okay? If you do that, all of these t becomes tau. This is d over d tau, tau, tau. This becomes 1, and you just get a t here. Right? And so now the inf is somewhat more easy to do because it's explicit in the objective rather than being in the boundary. Okay? And now think a little bit about what you need to do here. Right? Let's look just at the soup. Okay? Clearly, the soup of this object is always bounded from below with the soup at h equals 0, because I'm adding a constraint. Okay? If you convince yourself, if you think a little bit about it, you will realize that this is the only way you can actually achieve then the inf, because if you don't get h going to 0, you have this guy there that's hanging around, that otherwise you could use to make that the whole thing goes down to minus infinity, which it can't do because it's a convex optimization problem. Okay? At least at the level of theta. Okay? And because of that, you did use this. And I'll show it to you on examples, what that means. Bear with me. That's after the break. Okay. So now I want to, I have like very little time, but I wanted to show you that, that you don't need to do path integral and all that to derive this. So let me try to go quick on this. So I told you that you can solve this equation. I'm not going to put an epsilon on it. The epsilon has appeared now. That if you solve this backward equation, then u epsilon at 0x is this thing that we started to calculate. Remember, that was the meaning of the backward Kolmogorov equation. Yes? Right? All right. Now, you see that the statement that we have made before is that we know from, or we suspect that this guy, that this limit exists. Okay? Because that's the large deviation statement that we did. So if we know that this limit exists, let's try to deduce what it is. So, let's call this v of tx. So to do that, let's just change variable here. And what I'm going to do is you rewrite this. What I'm doing here is something that you're also very familiar with. It's WKB type expansion. Let's do that. Okay? I'm changing variable. Instead of using u as a variable, I use v. Right? If you put that in the equation, let me write down the result very quickly. You get, okay. This dt brings down a 1 over epsilon dt v epsilon and then the exponential. I'm going to factor that guy because it will appear in every term. The b does the same thing and you get a v. This guy brings you two terms. One is when you take the Laplacian is the divergence of the grad gives you a 1 over epsilon grad of this. And then if you take the grad again, you get a term of order 1. But since I have, let me write them in the right order. This is an identity. If you can't, I mean, when you take this guy and you do these ansatz, what you end up having is this equation where there was a 1 over epsilon here because you take twice the gradient of this, but there is no 1 over epsilon here. Since I put 1 over epsilon, you get this. Yeah? Yeah. Yes. You can't do that because of maximum principle. Everything is positive. Yes. All right. So now, okay, so now let's be brutal, and that's actually something that, of course, needs to be justified on a case-by-case basis. But if you look at this equation, let epsilon go to 0, drop this. And say, oh, what does V? This guy doesn't matter, right? And so then you get the following equation for V. So in the node that I'm going to give you, there's a little bit of explanation. This guy you recognize. This is the Hamilton-Jacobi equation. In the classical mechanics, for the action, right? And you can rewrite that here. It's an Hamilton-Jacobi equation where you have the standard way you write the Hamilton-Jacobi equation is by writing it. What is this? This is exactly the Hamiltonian that we derived before. For this case, is the Hamiltonian which is not evaluated at x and theta, but at x and grad v. Yes? And in fact, why that is because if you want to solve, you can solve this equation by the method of characteristic because it's first order. How do you solve this equation? What are the characteristics? The Hamilton's equation that we have seen before. Right? And how do things vary along the characteristic? Let me write this here. Well, the gradient of v of t along the characteristic, where xt here is the solution of the Hamilton's equation, is t. And if you, along the characteristic, this guy just reduces to 1/2 sigma squared. So you can integrate it. And you recover exactly the same result as the one that we derived by the path integral. Yes? Okay. So why does that matter? And I have like 10 minutes to do it, so I'll do something which will look a little bit, maybe I'm going to give you an example in the next class. Okay? So bear with me. So I want to show you that this path, all of what I write here, applies to a much larger class of problem than the one where you have diffusion with small noise. Okay? And to convince you of that, I'm going to look at one example. And I have 10 minutes to do it, and then we're going to go back to examples in a minute. Okay. So I'm going to look at Markov jump processes, which, okay, so, I mean, this is the closest we're going to get to, I guess, spin glasses, right? Isn't that what they're supposed to be? So we're going to look at Markov jump processes. And so we're going to look at something where these are reaction channels. Okay, and each of them, so there's an xt that lives in a discrete space, so it's a discrete variable. For example, it could be on zd or on nd, whatever. Think spins, for example. Okay, they're discrete. And then there are reaction channels. As I say, I'll give you an example in the next class, right? And each of them has a rate which is, I will denote by lambda j of x. So it depends on the position where the process is. Okay, and this guy is, bigger or equal to 0. And it's associated with a change vector which is nu j, which has the property that if if x belongs, so this is a discrete state space, let's call it S. If or omega, maybe better because I will need S data. If this guy belongs, you need to have that, you remain in the space. Okay? You could imagine that this is a random walk on a graph, which is always what it is, but also for spin system, you can write them down like that. I'm going to show you reaction diffusion for discrete variables that are of this type. Okay? So what is this dynamics? What it says is that, essentially, it says that x at time t plus delta t, given xt, is nu j with probability 1 minus delta t. So it says, if you say this is the rate of change, and they are all happening independently, okay, then you deduce that the probability, this guy, okay, will be x of t plus nut j with probability, that is equal to that. And that's true for every j. And then it's equal to this if no reaction occur, and that's with probability, this is with small probability, and this is with the probability, my apologies. What is this saying? If you take an interval of time sufficiently small, okay, the probability that two or more reaction occurs goes to 0 faster than delta t. The probability that one reaction occur, say reaction J, goes to 0 like delta t, and this is its probability. That's the meaning of what these rates are. And of course, that means that with probability 1 minus all of what's happening here, you get that there is no change. Yes? So notice that this means that if you take a test function g of xt, and you look at time t equals 0, okay, what will that be? It will be, it's going to be this. Is the sum for j equal 1 up to r, t is the same as delta t on the line above, of so this is, I'm looking at this guy, and I take the expectation conditional on this is x at time t equals 0 is equal to lowercase x. So what you get is this. That's the probability that something changed. And then you have plus 1 minus delta t times the sum from j equal 1 up to r of lambda j of x times g of x. Yes? But this means that if I subtract from this g of x, right, I just killed that term. And that means that now I can take 1 over t. So this guy disappears. Yes? And it means that what I have obtained, we're almost there. Is that the L of Gx, what is the generator on this system? It's simply this. You're probably more used to write this generator like the adjoint of it, which is the one that enters the equivalent of the Fokker-Planck equation would be the forward master equation. This is the backward, right? That's the generator. I have this, okay? Now I have 5 minutes, and I'm going to show you examples. So let's imagine here. So okay, so in this guy here, there is no the noise is completely intrinsic. There is not a deterministic part and a stochastic part, right? So there is not something that is deterministic where I can say that this is O1 and then I'm going to put a little bit of noise on top of it. But here is something we can do, and I'll show you example. We can imagine that after rescaling of your system, things are happening fast, but leads to small changes. And I'll show you exactly what that means in the example. So fast rates means I'm going to put a 1 over epsilon here. Small changes, I'm going to put an epsilon there, right? So we're going to look. This is not this this is the process where you would get a 1 over epsilon here and an epsilon there. Okay, and then put them everywhere. And then you would get, that you get the 1 over epsilon here and the epsilon there. Yes? Okay, 2 minutes. This is the backward Kolmogorov equation for this variable that depends on epsilon. And let me write it. I have 10 minutes actually. Let's slow down a little bit. This is the backward Kolmogorov equation, right? This tells you how observable evolve. If I solve this equation, you know how to calculate expectation of observable on this system. It's exactly the same as before, right? Okay, so let's look at this. Suppose that we look at this with an initial condition, or a final condition, which is just an f of x. No epsilon here in the final condition, right? Then we can take epsilon going to 0 here. Yes? Let's try to take epsilon going to 0. Okay, we have 10 minutes. I'll try for the last 10 minutes, we're going to do this class interactive. What is the limit of epsilon going to 0 of this equation? There's 1 over epsilon here. There's an epsilon there. What does that converge to? Yes. Right? The first order term disappears. The next order term is just the grade. Remember that this is a vector, right? It's a vector of change. So you get nu j times the grade on u. Right? Yes? So you get this limiting equation. But that's the backward Kolmogorov equation of no more epsilon. I've taken the limit. That's the backward Kolmogorov equation of what? We have seen it before. If you were to write down the backward Kolmogorov equation, not of an SDE, but of an ODE, if there was no noise, right, you would get something in which there is a first order derivative instead of a Laplacian. Yes? Well, this is, I can write it here, then I'll erase. Okay, so this means that these are scalar, and this is the vector. This is the equation that you get. This is the law of large number in this system. This is the equation of x dot equal b. Okay? I'm going to show you example of this that involve chemical kinetics plus diffusion. But for chemical kinetics, you know this. This is what's called the law of mass action. We'll see that in the next class. Okay, bear with me a little bit. But you have gotten this. Now, this ODE can have exactly the same behavior as the one that I have shown before, which is that it's not in gradient form. This is not the gradient of an energy. So, it's complicated. And it could have multiple fixed points. The example I'm going to show you have that feature. If you have multiple fixed points here, then that means that the noise can push them from one to the other. By noise, that means what? That means fluctuation. Fluctuation, that means what? That means, well, what happens if this epsilon is not 0, which we will relate to system size. Okay, this what I've done here is really a mean field limit. How can we deduce what to do? And now is really the end. How can we deduce what to do to go to large deviation? Well, we can do exactly the same calculation as the one that we have done, for SDE. Let me write it quickly, and then I'll let you go to coffee. Let's imagine that we look at now I've put this ansatz. So if you do that, you can do let's look at a solution like this. Let me write down what the equation that you get. So if you plug this ansatz, which is consistent with the boundary condition, into this equation, this dt of u epsilon gives you a 1 over epsilon e to that times dt of v epsilon tx. Then I already had there is no derivative here, as you notice, and I already had a 1 over epsilon, so I can take it out. Okay? But now I need to write this. Okay, and now, so here what do I have? If I want to factor that guy, let me write it, and then we see if you agree. Because this guy is just this. But then, if I want to factor this quantity out, I need to subtract it here. And then, what is this one? Well, it's just that, if you put this one back in. Yes? So now this is equal to 0. Right? Okay, what's the limit of this equation? Forget about this. And take epsilon going to 0. You get this. And there's a little something that's happening here, which is it's the same calculation as the one we did there. Right? Except that the 1 over epsilon, this minus that, has now been popped up into the exponential. Right? And so that means that when you take the limit, you get this. You get something which is similar as what we had before, except that it's there. Yes? But this is an Hamilton-Jacobi equation. It's an Hamilton-Jacobi equation with which Hamiltonian? Let me write it as a function of theta. Theta is really grad V. The Hamiltonian is just the one that you read above. I don't know where there's a minus. There's no minus. This is the Hamiltonian. Okay, we're going to discuss this in the next class. A few comments about it. It's a convex function of theta. You can verify this. 1. Yes? It's not a quadratic function of theta. You notice that this is where I'm a physicist by training, so I can say bad things about physicists. Okay? If you're a physicist here, I'm not going to even say a bad thing, but if you're a physicist here, what could you do? You'd say, oh, why do you stop here? Take the next order term. The next order term would give you a diffusion, right? And now you say, but if I have a diffusion, then instead of writing this ODE, I could write an SDE. If you have this SDE, you could write down the large deviation principle associated with it, and we are back to what we have discussed for most of the class. This is telling you, well, actually, if you do that, you get the wrong answer. Because when you take the limit properly, you don't get a quadratic Hamiltonian, which is obviously what you would get if you were to do this second-order expansion. In fact, the second-order expansion would amount to taking this Hamiltonian and expanding it in theta, and only keeping the first two terms. non-trivial, which would be nu j times theta, which in fact give you this as the law of large number, and then you would get 1/2 nu j times theta square, which is the noise. This is what is sometimes called the chemical Langevin equation. And it's a valid equation that you may use, for example, to do CLT type argument, small fluctuation. But if you want to understand large deviation, there is no free lunch. You need to use this one. Okay? And I have kind of indicated for you why. Right? Now, this is why this Hamiltonian formula is also easy, useful. If there are more than 2 reactions, you cannot solve this. You cannot take the Legendre transform of this explicitly. Quadratic Hamiltonian, you can do Legendre transform because you just need to solve a linear system. But this becomes a nonlinear system of equations that you need to solve if you want to do the Legendre transform. So this is a case where the Hamiltonian is available to you, but not the Lagrangian. Okay? And if you want to understand large deviation here, again, you really need to look at this. Okay? So I'll stop here, and then after the coffee, I'm going to revisit all this and try to make it a little bit less dry just by going through examples where we can do this calculation explicitly, and I will really show you pictures where you see what are the flows, what are these things, what is the Hamiltonian, what is H equals Z, etc., etc. Okay?